Code section 250.92 addresses the use of grounding bushings in certain applications. Specifically, it states that when threadless couplings and connectors are used with metal raceways and metal-clad cables, an approved grounding bushing shall be installed between the coupling or connector and the raceway or cable. This requirement is in place to ensure electrical continuity between the raceway or cable and the connector. Grounding bushings play a crucial role in providing a low impedance path for fault currents, which is essential for proper grounding and safety. The purpose is to maintain a reliable electrical connection, even in the event of a fault. However, there is an exception to this rule outlined in 250.92-3. This exception states that grounding bushings are not required for threadless couplings and connectors where made up tight for metal raceways and metal-clad cables. The key here is the phrase "made up tight." This exception typically applies to set screw connectors, provided they are properly installed and tightened according to the manufacturer's specifications. When set screw connectors are correctly installed, they create a sufficient electrical bond, negating the need for a separate grounding bushing. It is critical to adhere to the manufacturer's torque specifications when tightening set screw connectors. Proper torque ensures a secure mechanical and electrical connection. Over-tightening can damage the connector or raceway, while under-tightening can result in a poor electrical connection. Let's consider the scenario where set screw connectors have been installed and properly tightened. In this case, the installation meets the exception outlined in 250.92-3, and grounding bushings are not required. The exception recognizes that a properly installed set screw connector provides an adequate grounding path. However, an electrical inspector might not be fully aware of this exception or may misinterpret the code. It is the inspector's responsibility to stay up to date on the NEC and its interpretations. Inspectors should have a thorough understanding of the code and its exceptions. An inspector's lack of knowledge regarding specific code sections or exceptions can lead to incorrect citations and unnecessary work. In the event of a disagreement with an inspector's interpretation, there are steps that can be taken to address the issue. Firstly, it is important to politely and respectfully explain the relevant code section and its exception to the inspector. Providing documentation, such as the manufacturer specifications for the connectors, can also be helpful. If the inspector remains unconvinced, the next step is to request a re-inspection and further explain the situation. It may also be beneficial to involve a more experienced electrician or electrical engineer to provide additional support and expertise. If the issue persists, the ultimate recourse is to contact the authority having jurisdiction, often referred to as the AHJ, for clarification. The AHJ is the governing body responsible for interpreting and enforcing the electrical code in a specific area. The AHJ can provide a definitive ruling on the interpretation of the code and ensure that it is applied correctly. It is important to remember that electrical codes are constantly evolving, with new editions being published every 3 years. Each new edition may include revisions, additions, and deletions to existing code sections. Staying informed about the latest code changes is crucial for all electrical professionals. There are several resources available to help stay up to date in the NEC, including codebooks, training courses, and industry publications. Continuous learning and professional development are essential for ensuring compliance with the ever-changing electrical code. In conclusion, understanding the exception to 250.92-3 is crucial when using set screw connectors. Proper installation and tightening of these connectors can eliminate the need for grounding bushings. In case of a disagreement with an inspector, clear communication, documentation, and, if necessary, involvement of the AHJ are essential for resolving the issue and ensuring compliance with the NEC. Now let's expand upon the NEC requirements for grounding and bonding to provide a more comprehensive understanding. Grounding and bonding are fundamental concepts in electrical safety. Grounding refers to the connection of electrical equipment and systems to the earth, while bonding refers to the connection of various metallic parts within an electrical system to create a continuous electrical path. The primary purpose of grounding is to provide a low impedance path for fault currents to return to the source. This lower impedance path helps to quickly trip over current protection devices such as circuit breakers or fuses in the event of a ground fault. Bonding, on the other hand, ensures that all metallic parts within an electrical system are at the same electrical potential. This reduces the risk of electric shock by preventing voltage differences between different metallic parts. The NEC contains numerous articles that address grounding and bonding requirements. Article 250 is the primary article that covers grounding and bonding in detail. This article provides specific requirements for different types of electrical systems, equipment, and installations. Some of the key topics covered in Article 250 include grounding electrode systems, equipment, grounding conductors, bonding jumpers, and grounding of specific equipment. Grounding electrode systems are used to connect the electrical system to the earth. These systems typically consist of one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes. The grounding electrode system must have a low resistance to earth to effectively dissipate fault currents. Equipment grounding conductors, often referred to as EGC, are used to connect the non-current carrying metallic parts of electrical equipment to the grounding electrode system. These conductors provide a path for fault currents to return to the source and trip over current protection devices. Bonding jumpers are used to connect various metallic parts within an electrical system to create a continuous electrical path. These jumpers ensure that all metallic parts are at the same electrical potential, reducing the risk of electric shock. Specific equipment, such as motors, transformers, and generators, also have specific grounding requirements outlined in the NEC. These requirements vary depending on the type of equipment and its application. In addition to Article 250, other articles in the NEC also address grounding and bonding requirements for specific types of installations, such as swimming pools, data processing systems, and healthcare facilities. It is important to consult the appropriate articles in the NEC for specific grounding and bonding requirements. Now let's look at more specific code sections related to the topic. Section 314.40 states that boxes shall be mounted so that the box is rigidly and securely fastened to the surface on which it is mounted. This is to ensure that the box is stable and can withstand the stresses of normal use. 314.40b says that boxes shall be of sufficient size to provide free space for all conductors enclosed in the box. This is to prevent overcrowding of conductors, which can lead to overheating and other problems. 314.40c notes that boxes shall be accessible. This is to allow for easy inspection and maintenance of the wiring in the box. 314.40d adds that boxes shall be identified for the purpose for which they are used. This is to ensure that the correct type of box is used for each application. Another relevant section is 314.40e concerning the support of boxes. Boxes shall be supported in accordance with the requirements of Article 314. This article provides detailed requirements for the support of boxes, depending on the type of box and the method of installation. Let's shift the focus slightly towards grounding electrode conductors. The grounding electrode conductor, often abbreviated as GC, is a critical component of the grounding system. Its primary function is to connect the grounding electrode, such as a ground rod or water pipe, to the electrical system's grounded conductor, typically the neutral busbar in the service panel. The size of the grounding electrode conductor is determined by NEC Table 250.66, which is based on the size of the ungrounded service conductors. The larger the service conductor is, the larger the grounding electrode conductor required. The grounding electrode conductor must be made of copper, aluminum, or copper-clad aluminum and must be continuous, meaning without any splices or joints, unless specifically permitted by the NEC. The grounding electrode conductor must be securely connected to both the grounding electrode and the grounded conductor in the service panel. The connection to the grounding electrode must be made using an approved method, such as a listed clamp or fitting. The connection to the grounded conductor in the service panel must be made using a listed connector or terminal. The NEC also provides specific requirements for the protection of the grounding electrode conductor. If the grounding electrode conductor is exposed to physical damage, it must be protected by conduit, armor, or other suitable means. The grounding electrode conductor must also be protected from corrosion if it is installed in a corrosive environment. In addition to the grounding electrode conductor, the equipment grounding conductor plays a crucial role in electrical safety. The equipment grounding conductor provides a low impedance path for fault currents to return to the source, thereby facilitating the operation of overcurrent protection devices. The equipment grounding conductor must be installed with the circuit conductors and must be sized according to NEC Table 250.122, which is based on the rating of the overcurrent protection device. The equipment grounding conductor must be made of copper, aluminum, or copper-clad aluminum and must be continuous, unless specifically permitted by the NEC. The equipment grounding conductor must be securely connected to the equipment grounding terminals of all equipment and appliances served by the circuit. The NEC also provides specific requirements for the identification of the equipment grounding conductor. If the equipment grounding conductor is insulated, it must be identified by a continuous green color or a green color with one or more yellow stripes. Now let's delve into the topic of bonding jumpers. Bonding jumpers are used to connect various metallic parts within an electrical system to create a continuous electrical path. This ensures that all metallic parts are at the same electrical potential, reducing the risk of electric shock. There are two main types of bonding jumpers: equipment bonding jumpers and main bonding jumpers. Equipment bonding jumpers are used to connect the non-current carrying metallic parts of equipment to the equipment grounding conductor. These jumpers ensure that the equipment is properly grounded and that fault currents can safely return to the source. Main bonding jumpers are used to connect the grounded conductor, typically the neutral busbar, to the equipment grounding conductor at the service entrance. This jumper provides the primary bonding connection between the grounded conductor and the equipment grounding system. The size of bonding jumpers is determined by NEC Table 250.102 cone, which is based on the size of the ungrounded service conductors. The larger the service conductors, the larger the bonding jumpers required. Bonding jumpers must be made of copper, aluminum, or copper-clad aluminum and must be securely connected to the metallic parts being bonded. The NEC also provides specific requirements for the installation of bonding jumpers. Bonding jumpers must be installed in a manner that minimizes impedance and ensures a reliable electrical connection. Now we'll discuss surge protection. Although it wasn't directly mentioned, surge protection is an important aspect of electrical system safety. Surge protective devices, or SPD, are designed to protect electrical equipment from transient voltage surges which can be caused by lightning strikes, utility switching, or internal events within the facility. SPD are typically installed at the service entrance, but they can also be installed at downstream panels or even at individual equipment locations. The NEC requires SPD to be installed in certain applications, such as in dwelling units and in critical facilities like hospitals and data centers. SPD are rated based on their ability to withstand surge currents and their voltage protection level. It is important to select SPD that are appropriate for the specific application and the expected surge environment. SPD must be installed in accordance with the manufacturer's instructions and the requirements of the NEC. Proper installation is critical to ensure that the SPD function correctly and provide adequate protection. Now let's transition to the concept of selective coordination. Selective coordination is a design practice that ensures that only the overcurrent protection device closest to a fault will trip, while leaving other upstream devices unaffected. This is important for maintaining power to critical loads and preventing unnecessary outages. Selective coordination is typically achieved by carefully selecting and coordinating the time current characteristics of the overcurrent protection devices. The NEC requires selective coordination in certain applications, such as in healthcare facilities and in systems with emergency power sources. Achieving selective coordination requires careful planning and design, as well as a thorough understanding of the overcurrent protection devices being used. Short-circuit studies are often performed to verify that selective coordination is achieved under various fault conditions. Now let's dive deeper into the different types of overcurrent protection devices. Overcurrent protection devices are designed to protect electrical circuits from excessive current, which can cause overheating, damage to equipment, and even fires. There are two main types of overcurrent protection devices: circuit breakers and fuses. Circuit breakers are electromechanical devices that automatically interrupt the flow of current when a fault occurs. They can be reset and reused after a fault has been cleared. Fuses are one-time devices that melt and break the circuit when a fault occurs. They must be replaced after a fault has occurred. Circuit breakers are typically used in residential, commercial, and industrial applications. They offer the advantage of being resettable and reusable. Fuses are often used in applications where high fault currents are expected, such as in motor circuits and in some industrial applications. They offer the advantage of being relatively inexpensive and providing fast fault clearing. Circuit breakers and fuses are available in a variety of sizes and types to meet the needs of different applications. The selection of the appropriate overcurrent protection device depends on the circuit voltage, current rating, interrupting rating, and other factors. The NEC provides specific requirements for the selection and installation of overcurrent protection devices. These requirements are designed to ensure that the devices provide adequate protection for the electrical circuits they serve. Now let's move on to the topic of arc flash protection. Arc flash is a dangerous phenomenon that can occur when a short circuit creates an electric arc. Arc flash events can generate intense heat, pressure waves, and toxic gases, which can cause serious injuries or even death. The NEC requires arc flash hazard assessments to be performed for electrical equipment that is likely to be energized while working on it. These assessments are designed to identify the potential arc flash hazards and to determine the appropriate personal protective equipment, or PPE, that is required to protect workers. PPE for arc flash protection can include flame-resistant clothing, face shields, gloves, and other specialized equipment. The NEC also requires arc flash warning labels to be placed on electrical equipment to alert workers to the potential hazards. Arc flash protection is a critical aspect of electrical safety and should be taken seriously by all electrical workers. Now let's talk about voltage drop calculations. Voltage drop is the decrease in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that voltage drop be limited to 3% for branch circuits and 5% for feeders. Voltage drop calculations are used to determine the size of conductors needed to maintain acceptable voltage levels. These calculations take into account the conductor length, current, and resistance. There are several online tools and software programs available to assist with voltage drop calculations. It is important to perform voltage drop calculations to ensure that electrical equipment operates properly and efficiently. Now let's move to harmonics. Harmonics are distortions of the normal sinusoidal waveform of alternating current, or AC. They are typically caused by nonlinear loads such as electronic devices, variable frequency drives, and arc welders. Harmonics can cause a variety of problems in electrical systems, including overheating of equipment, increased energy losses, and malfunction of sensitive electronic devices. The NEC does not directly address harmonics, but it does require that electrical systems be designed and installed in a manner that minimizes the negative effects of harmonics. Harmonic filters can be used to reduce the levels of harmonics in electrical systems. These filters are typically installed at the source of the harmonics, such as at the output of a variable frequency drive. Now let's discuss the requirements for electrical permits and inspections. Electrical permits are required for most electrical work, including new installations, alterations, and repairs. The purpose of electrical permits is to ensure that the work is performed in accordance with the NEC and other applicable codes and standards. Electrical inspections are performed by qualified inspectors to verify that the work has been performed correctly and that the electrical system is safe. It is important to obtain the necessary electrical permits before starting any electrical work. Failure to obtain a permit can result in fines and other penalties. It is also important to schedule an electrical inspection after the work has been completed. The inspector will verify that the work meets the requirements of the NEC and other applicable codes and standards. Finally, let's discuss the importance of safety training for electrical workers. Electrical work can be dangerous if not performed properly. It is important for electrical workers to receive adequate safety training to protect themselves from hazards such as electric shock, arc flash, and falls. Safety training should cover topics such as lockout/tagout procedures, use of personal protective equipment, and safe work practices. Regular safety meetings and refresher training are also important to reinforce safety knowledge and skills. Safety should always be the top priority when performing electrical work. The information provided is intended for educational purposes only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or electrical engineer before performing any electrical work. The National Electrical Code, or NEC, is a comprehensive set of standards that govern the safe installation of electrical wiring and equipment. It is updated every 3 years, and it is essential for all electrical professionals to stay current with the latest edition. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, bonding, and equipment installation. It is important to consult the NEC for specific requirements related to any electrical work being performed. In addition to the NEC, there may be other applicable codes and standards that must be followed. These may include local building codes, state electrical codes, and industry standards. It is important to be aware of all applicable codes and standards before starting any electrical work. The proper design, installation, and maintenance of electrical systems are essential for ensuring safety and reliability. By following the requirements of the NEC and other applicable codes and standards, electrical professionals can help to prevent electrical hazards and protect people and property.